Welcome to the deep dive. We're your shortcut, really, to getting genuinely well-informed without, feeling overwhelmed. We try to help you gain knowledge quickly, thoroughly, and hopefully get those aha moments that make things click. Today, we're diving into something pretty specific, but really foundational in, well, industrial control. It's a building block called ETFFSR, and it operates within this international standard, IEC 61499. Sounds technical, but we'll break it down.
Yeah, and IEC 61499, it's more than just a name. It's a global standard for modeling these distributed industrial control systems. Think of it like the master plan for how complex automated processes talk to each other, often across, lots of different devices. And the heart of it, these things called function blocks or FBs, they're basically like the Lego bricks for building control logic, really fundamental.
Okay, so like Lego bricks. I like that. And this specific brick, ETFFSR, our mission today is to really understand it, right? It's called an extended function block, and it's got beastable behavior, so two stable states and toggle functionality. But we want to kind of strip away the jargon, see how this simple block is maybe the secret sauce in some really robust systems. We'll look at its structure, how it actually behaves, and importantly, where you might see this thing in the real world. So maybe let's start right at the beginning. Its structure. Our source material calls it a basic function block, a BFB. What does that tell us about how it's built?
Right, basic function block, or BFB. Well, the name gives it away, but it's foundational. It's defined mainly by two things. It's external interface, that's how it connects and talks to everything else, and it's internal logic.
Yeah.
And that internal logic, it's laid out very precisely by something called an execution control chart, an ECC. Plus, there's specific algorithms, little bits of code that run when certain things happen.
Okay, the interface. That sounds like events coming in, variables going out. Can you sort of walk us through that for the ETFFSR?
Absolutely. So for event inputs, it's got three main ones: S, which stands for set, R for reset, and CLK for clock. Each one triggers a specific action inside the block. Then going out, there's one key event output called EO. This one fires off whenever the block's main output changes state. And that main output, it's a variable called Q. It's a Boolean true or false representing the current state of our little flip-flop here.
Got it. So specific inputs trigger actions and an output signals change. How is this event-driven thing different from, say, old-school PLC programming, the scan-based stuff? What's the advantage, especially for these distributed systems you mentioned?
That's a really key difference. In a traditional scan-based PLC, the controller just runs through all the code top to bottom over and over again. It checks all inputs, calculates everything, whether anything's changed or not. IEC 61499, with its event-driven approach, is much smarter, you could say. A function block only does work when an event arrives at one of its inputs. This is way more efficient, particularly when you have lots of devices spread out. It cuts down needless processing. And it lets different parts react precisely when needed. It's more reactive intelligence instead of just constant checking.
Okay, that efficiency aspect makes a lot of sense. Now, inside the block, you mentioned this execution control chart, the ECC, dictates behavior. What are the main states this ETFFSR block can be in?
It mainly lives in three states. There's start, that's its initial state, when it first powers up or gets initialized. Then there's set, which it goes into when that S event comes in. And finally, reset, which it enters if the R event arrives.
Okay, start, set, reset, pretty clear. How does it move between them? Is it just S takes you to set or S takes you to reset? Or is there more to it?
It's mostly like that, but with a twist for the CLK input.
Yeah.
So from start, S takes you to the set state. If you're in set and R happens, you go to reset. Makes sense. If you're in reset, S happens, you go back to set. Still following. But here's the interesting part, the toggle bit. The CLK input also causes transitions. If you're in the set state and CLK arrives, it transitions you to reset. And conversely, if you're in reset and CLK arrives, it transitions you to set. It flips the state.
Whoa, okay. So S and R are like direct commands, but CLK just flips whatever state it's currently in.
Yeah.
That's actually pretty neat, the ultimate toggle. And you mentioned algorithms, little bits of code running during transitions. Is that what sets the output?
Exactly. Those algorithms are very simple. Very direct. When the block enters the set state, an algorithm runs that just sets the output variable Q to true. And when it enters the reset state, a different algorithm runs that sets Q to false. And crucially, right after Q changes value either to true or false, that EO event output gets triggered. And EO isn't just like a notification. It's the signal that tells other connected function blocks, hey, something changed, maybe you need to do something now.
Yeah.
It propagates the change. I see. So it's not just saying, I've changed, it's actively triggering the next step, potentially. Does that mean the The timing and reliability of that EO event are super important. Are there built-in guarantees in IEC 61499?
Oh, absolutely critical. It is the trigger for the next step in many cases. And yes, the way IEC 61499 defines the execution model with these ECCs and the event handling, it's designed to be deterministic. That means you get reliable, predictable propagation of these events. You know how the system will react and when. That's why it's trusted for, serious industrial applications. Right, predictability is key there. This sounds incredibly useful. So where would we actually, see this in action? Can you give us some concrete examples?
Sure, because it can store a state, set or reset, and also toggle. It pops up in quite a few places. Think about a bottle filling line in a factory. You could use an ETF FSR to track if a bottle is in position. A sensor sees a bottle, triggers the S input, that sets Q to true bottle present. The filling process can then start. Once it's filled and moves on, maybe another sensor or timer triggers R, setting Q back to false. Simple state management.
Okay, like a memory bit for bottle here. What about the toggle part?
Right, the toggle.
Yeah.
Imagine maybe a sequence for a robot arm on an assembly line. You could have just one button connected to the CLK input. The operator presses it once. That toggles Q to true, maybe starting the robot's pick-and-play sequence. They press the same button again, it toggles Q back to false, perhaps halting the sequence safely, or maybe signaling it's done and ready for the next part.
Ah, so one button does double duty, start and stop, or cycle through steps. That definitely simplifies the controls for the operator.
Exactly. Instead of needing separate start and stop signals wired up for that specific function, one clock pulse toggles the state. It's elegant. It reduces complexity in many real-world control sequences.
So it's good for managing these kinds of actions, these states, but also maybe for time things, using that CLK input more like a clock.
Precisely. If you need something to change state regularly, maybe synchronize with other processes, you feed a periodic clock signal into that CLK input. Every rising edge, or however it's configured, it just flips the Q output. On, off, on, off. Think of, I don't know, flashing lights or maybe disabling something periodically in a test sequence. It gives you both event-driven control and clock-driven toggling in one small package. And what's really cool, I think, is how this ETF FSR block kind of perfectly shows what IEC 61499 is all about. It's got a really clear structure, simple rules for changing state. But it's incredibly versatile. It really highlights how you can build these complex, reliable control systems from simple, reusable pieces, like those Lego bricks we started with.
Yeah, that's a great summary. So we've seen this one block, ETF FSR. Seems simple on the surface, but it can manage state holding it with set and reset. It responds to specific events, and it can even just toggle its state back and forth using that clock input. So useful for remembering things, reacting to triggers, or even running time sequences. It makes complex automation feel, well, surprisingly elegant, doesn't it? Yeah.
It really does. And that leads to a thought, maybe for you listening right now. When you understand these fundamental building blocks, these elegant little components like ETF FSR, you start to see how incredibly complex, robust, automated systems get built. Systems that run factories, power grids, all sorts of things. So the question maybe is, what other seemingly simple, reusable components are hiding in plain sight? What are the fundamental building blocks quietly running the complex technology you use every single day? Maybe something to think about.